Welcome back to the deep dive. Today, we're diving into something truly fascinating, maybe one of the universe's biggest mysteries: black holes.
Absolutely. They're these incredible cosmic objects, right?
Right.
Places where gravity just goes completely off the charts, bending space and time itself.
Exactly. And, they feel like science fiction sometimes, but they're very real. We've been looking through A Simple Guide to the Cosmic Mystery and some recent research notes.
Yeah, trying to piece it all together.
We want to unpack for you what these things actually are, how they even form, and some of the latest really mind-bending discoveries coming out.
And it's so important to get into this because understanding black holes, well, it's key to grasping the really extreme physics that govern our universe.
Right?
They're not just weird outliers. They're fundamental players in how cosmic structures like galaxies actually evolve. They push our theories to the absolute limit.
Okay, so let's start with the basics from the guide. When we talk about a black hole, it's not like an empty hole in space, is it?
No, not at all. It's actually the opposite. It's an unbelievable amount of mass crammed into an incredibly tiny space.
Like, imagine taking a star way bigger than our sun and squishing it down.
Exactly, squishing it down to just a few miles across. That extreme density creates what we call a singularity, theoretically, a point of infinite density.
And that crazy density warps space-time so much.
So much that the gravitational pull becomes immense. Basically, the escape velocity needed to get away is faster than the speed of light.
Which means nothing can escape, not even light, hence black.
Precisely. And where do they come from? Well, the guy points out that most of the ones we observe are stellar black holes.
The leftovers of giant stars?
Yeah. When a really massive star runs out of fuel, its own gravity causes it to collapse
Yeah.
catastrophically.
Sometimes you get a supernova, right? A big explosion.
Often, yes. But the core keeps collapsing inwards, shrinking down until it forms that stellar black hole.
And the guide mentions they're not all the same size. We have these stellar ones, maybe a few times the mass of our sun.
But then you have the supermassive ones.
Those are the monsters, right? Millions, even billions of times the sun's mass.
Billions, yeah. Found lurking at the centers of most big galaxies. We even have one, Sagittarius A, right at the heart of our own Milky Way.
And people are looking for others too, like intermediate ones.
Right. Intermediate mass black holes are a hot topic, and there's even speculation about primordial black holes formed way back near the Big Bang. Still theoretical, mostly.
Okay, so what if you actually got close to one? The guide talks about the event horizon.
Ah, yes, the event horizon. That's kind of the boundary, the point of no return. Once you cross it, you can't get back out because the escape velocity is higher than light speed.
But it's not like a vacuum cleaner sucking things in from afar. That's a misconception, isn't it?
It really is. Gravity is powerful, sure, but it behaves like any massive object. You only fall in if your path takes you too close inside that horizon. Planets orbit our sun without falling in, same idea.
And weird things happen with time too, time dilation.
Oh, absolutely. As you get closer to the event horizon, time for you would appear to slow down dramatically compared to someone watching from far away. It's a core prediction of Einstein's relativity.
So if we can't see them directly, how are we so sure they're, real?
Great question. We see their effects. We can track stars orbiting something invisible but incredibly massive at the galactic center, for example.
Like watching planets orbit the sun, but the sun's invisible?
Kind of, yeah. Or we see matter getting pulled in, heating up, and emitting X-rays just before it crosses the event horizon. And of course, there was that amazing image in 2019.
The picture of the black hole's shadow.
Exactly. Direct visual evidence. Plus, the 2020 Nobel Prize in Physics partly recognized the work confirming the supermassive black hole in our galaxy. The evidence is really solid now.
And the recent research notes we looked at mention even more ways we're detecting them now.
Definitely. The detection of gravitational waves back in 2015 was huge. LIGO and Virgo detected ripples in spacetime itself, caused by pairs of black holes merging.
Wow. Ripples in space-time.
Yeah, it opened a whole new window. But maybe the biggest puzzle right now, highlighted in those notes, is the information paradox.
Okay, explain that one. It sounds complicated.
It is. So Einstein's theory, general relativity, suggests that when something falls into a black hole, it's gone forever. The information about it is destroyed.
Okay.
But quantum mechanics, our other fundamental theory, has a strict rule. Information can never be truly lost. It has to be conserved somehow.
So the two big theories clash, right at the edge of a black hole.
Precisely. It's a major conflict.
Yeah.
And the latest ideas are exploring ways maybe the information isn't destroyed, Perhaps it's somehow encoded on the event horizon, or maybe it gets out later when the black hole evaporates, very slowly,
Hmm.
via Hawking radiation.
That's definitely pushing the boundaries of physics.
It really is. It
Yeah.
forces us to rethink everything.
So to wrap this up for you listening, black holes are these extreme regions of gravity, warping space-time itself. They're real, they shape galaxies, and they mess with time.
Absolutely. They're not just curiosities out there in space. They are fundamental tests for our deepest understanding of reality, challenging our core ideas about space, time, and information.
They really force us to confront the limits of what we know.
They're central to figuring out how the universe works at its most extreme levels.
So here's something to think about until next time. If that information paradox gets resolved, if information isn't actually destroyed by black holes, what does that tell us? What could that imply about the fundamental laws of physics, maybe even about the nature of reality itself?